Hello everybody, thank you for joining us today. My name is Minim and today we're going to be looking at the Big Bang Theory, which really talks about the start of the universe. So some of our learning objectives include to define the Big Bang Theory, to understand and explain evidence for the Big Bang Theory, and that includes the redshift effect and CMBR, which is commonly known as cosmic microwave background radiation. So if we're ready, let's get right into it. Okay, now I have a lot on the screen here, but don't worry, by the end of this video you're going to understand everything that's here. So straight away you need to understand something called the Big Bang Theory. So this is the theory that scientists generally accept now for what actually created the universe around us, right? So that it really tells us that the universe initially came from an initial singularity. That's just a fancy physics way of saying a single point, right? That expanded outwards. Okay, so the Big Bang Theory really tells us that first there was nothing. And then there was a tiny, infinitesimally small, that's why we call it a singularity, because we're really talking about a single point, when in reality it's really difficult to get single things, right? We had an initial single point and then all of a sudden it just expanded outwards in all directions, right? I'm going to try and do this as best as I can, up and down as well. And that in it eventually expanded until enough time passed for our little bubble of the universe to be born. Okay, so that's the Big Bang Theory. Now, there are two massive pieces of evidence for this that we need to understand. The first one is called the redshift, okay? So let's actually have a look at what redshift actually is. Over here in, say, figure 1, or let's just call it figure A, right? I have something called a spectrum, okay? So this is a spectrum. So a spectrum is a fancy physics word of saying something which displays the entire range of colors. Okay, so if we were to take a satellite take a telescope and point it out into the to the entire universe, right, and we were to take a picture and we were to feed it through some software, right, it would present us with this, right, a spectrum of colors. Okay, so all the colors that the telescope could see would be displayed here. But what astronomers found was that throughout the colors there were also these bands of black that represented missing colors, so colors that they couldn't see out in the universe, right? Well, why is this? Well, this is because some elements absorb some types of colors, right? At A level, you start to learn more about this. You start to learn about energy shells and wavelengths and all sorts of exciting stuff. But for now, you just need to understand that throughout these spectrums, there were some missing colors due to elements absorbing these colors. Okay, so this is our lab source, all right? So this is the source that we observed here on Earth. Then, if we point it at another place in the universe, so galaxy A here, right, we find that the same combination of same combination of missing colors, right? So where the black lines are, so you can see here we have 4 black lines, 2 kind of distantly apart and 2 close. Those same patterns of colors were shifted to the right, towards red. Okay, you can kind of start seeing why redshift is happening. So let's think about this here. Indigo has the smallest wavelength, so let's do that in green. Remember, lambda is the symbol for wavelength. This is the smallest wavelength, and red has the longest wavelength. So we can see if things are shifting right along the spectrum, that means that their wavelength is increasing. So wavelength is increasing as they go around. So wait, hold on a second. Why are the same exact pattern of black lines being shifted towards the right? And then if we look at another galaxy, galaxy B, which is even further away than galaxy A, we find that the same black lines have been shifted even further to the right. Their wavelength has increased even more. So eventually, scientists were able to get enough data, because that's what we do as scientists, right? We gather data and then we plot graphs, right? They were able to plot the distance of a galaxy, right, and it gave us something like this. All right, it gave us a straight line pointing away, right? And what did they plot this again? Well, they plot this against something called receding velocity. So this is sort of the speed at which they're moving away from us, right? So let's write that down. Speed at which they meaning galaxies are moving from us. Okay, so now we know that the further galaxies are away from Earth, the faster that they're moving. So this means that the source, so let's put that in blue, right? The galaxy is moving this way and it's emitting wavelengths. After a long time, right, when the galaxy moved away, the wavelength of the light that it's emitting starts to stretch. it starts to redshift. It starts to shift towards red. Okay, so moving objects lead to wavelengths of light stretching. Right, the wavelengths are therefore redshifted. So this is how we know that the universe came from a single point and started expanding outwards, because we've actually detected redshifts. Right, we know that the only way something can redshift is if it's moving away from us. So that, and with all of our data and our graph here, we know that galaxies are moving away from us, and they're moving away from us as faster. There's actually something really important there for your or if you do A level, right? That's something called dark energy, which is what makes them go faster. But I'm going to leave that for now, right? We know that the galaxies are moving away from us, therefore that their light is being redshifted, and that again reinforces the point that the universe expanded outwards. Okay, if something expanded outwards, think of it like a balloon being blown up. Every time it expands, the balloon gets blown up. Now let's have a look at the reverse. Let's go back in time. Our balloon gets smaller and smaller and smaller and smaller and smaller and smaller and smaller till we get to a single point, singularity, which is what the Big Bang talks about. All right, that the fact that we came from a singularity. Now let's have a look at something else called CMBR. All right, cosmic microwave background radiation. In the initial singularity here, this singularity must have had a huge amount of energy, right? Well, obviously, because it created the entire universe around us, right? And we know that energy can neither be created nor destroyed. So all of the universe energy must have been in that single point right there. So let's write that down. Energy must have been there, right? So the initial energy, what's the highest frequency and shortest wavelength wave of EM radiation? Well, that's gamma rays. So the highest energy rays must have first been gamma rays, which let's do in green. Oops, took away the Y. So the initial rays must have been gamma, which have high hertz, so frequency, and low lambda. Okay, eventually those gamma rays would be sent out into the universe, and they would increase in wavelength, right? They would redshift, because that makes sense, right? The initial single point of the universe, that must be the furthest thing away from us right now, right? So that must have the greatest amount of redshift. So it should have gone from gamma, let's do this in a different color. It would have gone from gamma, the shortest wavelength, to microwave by now. Okay, so scientists' calculations tell us that eventually it might even reach radio waves, but that won't be for billions of years, right? So scientists have worked out that the redshift should have led to the waves, the initial waves turning from gamma rays to microwaves, and that's what we've actually detected. We've detected everywhere in the universe we get faint microwave signals, and these signals are called CMBR, cosmic microwave background radiation, right? Cosmic meaning coming from the universe, microwave because that's what they are, microwaves. Background radiation meaning because just like normal background radiation such as alpha, beta, gamma, it's always present in the universe. Wherever we go, we can't escape it, right? So that also gives us evidence for the Big Bang theory, okay? Because if the universe initially came from a single point, no single point must have had gamma waves. Those gamma waves must have redshifted to microwaves by now, and that's what we've detected. So that was a lot of information, but if you go through this again slowly and work through all the logic as I tell you to do all the time, and then do questions, I'm sure you'll understand it perfectly fine.